Okay, next we're going to talk about probability distributions for discrete random variables. And to help set this up for us, let's take a look at this diagram that we saw at the very beginning of the course. So just to review, we have this population of items or objects, and it's very, very large. It's hard to get at every single item. One thing about this population that we might be interested in is a numerical summary measure called a parameter. In this case, I drew out the Greek letter mu for the population mean. So again, since all items are so difficult to get at in the population, what we do is we try to take a representative sample of those items. And the sample now consists of a smaller set of items that are much easier to work with. Again, in the sample, we might calculate a numerical summary measure called statistic, perhaps, for example, the sample mean. And then using this information that we have in the sample, we try to draw inferences back to what's going on in the population. Now, with respect to this population, we're going to want to start characterizing it with what are called probability distributions. And what these probability distributions represent is basically how items are distributed, at least in the in like a numerical sense, in terms of what the actual characteristic values are, such as GPA values. We're going to look at how those GPAs, let's say, are distributed. Do we have a lot of them that are between 3.5 and 4.0, or maybe a small amount? And we characterize how they're distributed with probabilities. So let's look at a very simple example to help explain this. Suppose we have numbers on slips of paper. So for example, here we have the number 6. We have, oops, actually that was the number 9, excuse me. We have the number 5. And we have basically slips of paper with numbers 0 through 9, the integers written on them. And what we like to be able to do is actually sample 50, repeat a sampling process 50 different times. So perhaps I have all the numbers here in this hat, and I'm going to randomly not look. I'm going to randomly select an item and not look at what I'm selecting, and this time I got a 0. Now I'm going to put this back in the hat. I shake the hat up again, and this time, oops, I accidentally looked, but let's say I didn't, and I got the number 1. And so we're going to do that 50 different times. Now, since we have just 10 numbers here, and they're all on individual slips of paper, and as long as I'm randomly selecting a number there, we can say that the probability of selecting a 0 is equal to 10%. Probability of selecting a 1 is equal to 10%. The probability of selecting a 9 is equal to 10%. And so let's actually look at how we can actually then simulate this process in R. So I come back over here to 10. So what I'm going to do is create an object called X that's going to have the values of 0 to 9 in it. Remember that the colon in R represents the word to, T-O. And then we're going to use the sample functions for us to simulate this drawing out of a hat process to allow us to take the sample. So I say sample, and what do I want to sample out of? Well, this 0 to 9. How many do I want to sample? 50. And I want to do it with replacement, meaning this is like putting those numbers back in the hat after you draw them out. So let me go ahead and execute that code. I'm going to use the head function with it as well, so we can see the first 6 observations that we get. And we can see the first time we got a 1, the next time we got a 0, the next time we got a 5, and so on. Now, if I were to run this exact same code again, look what happens. I get a different set of numbers. If I did it again, I get a different set of numbers. If I did it again, I get a different set of numbers here. Now, oftentimes you like to be able to reproduce this process of the exact same process of selecting these numbers and always get the same numbers. This is often helpful, like in a teaching situation like this. And so to do that, I'm going to do what's called set a seed. So whenever you're working with random selection of values, R or any other software package has some internal mechanism that's used to randomly select. the items. And it's based upon, this random selection is based upon a seed number. And if I set the seed myself, I can always reproduce what numbers are chosen. And so if I run this a few times, indeed you see that I do get the exact same values every single time. And we can take a look at a histogram of all those values too. So I'm going to just use the hist function with set1, put a title on it, put x-axis label, and also I'm going to include a specific set of values for breaks. What this is going to allow me to do is control where those classes are formed on the x-axis. Now, what I would like you to try on your own is to see what would happen if you wouldn't specify the breaks here. And what you're going to see is one little problem that R has when dealing with discrete random variables in a relatively small sample size. By specifying these particular breaks here, everything will work out just fine. So if I hit run there, and let me find my plot. I'm actually on a different monitor. And here we go. So 5 times I got a 0. 6 times I got a 1. 5 times I got a 2. And so on in this particular sample. So this takes us to page 3. Now you might be thinking, well, wait a second. You just told me that we would expect 10% of the time to get zeros, 10% of the time to get ones, and so on. Well, that's what's representing the probability distribution of the population. What we actually get for our sample can be a little bit different depending upon what our sample size is. Now, as we will see shortly, as that sample size grows, then what happens in the sample is going to be more representative of the population, and the proportions of times we get zeros, that we get ones, and we get twos in our sample is going to be much closer to what those population values are. We're going to let Y denote the number selected on a draw from 0 to 9. Note that this is a capital Y. You'll see why that's important coming up. In statistics, we call something like Y a random variable because it can change from, in this case, draw to draw in a random manner, which is controlled by a particular probability structure, such as I would expect 10% of the time to get zeros, 10% of the time I would expect to get ones. And so since we have this expectation regarding Y, what we can do is formally write out what's called a probability distribution for Y. And this is what it looks like. So the probability that Y is equal to 0 is 0.1. The probability that Y is equal to 1 is equal to 0.1 as well. And you can keep on going all the way down to the last value and write out the probability Y is equal to 9 is equal to 0.1. This is called a probability distribution. Now, if you notice here, I also have a lowercase y here as well. In statistics, especially when we want to define stuff formally, we always use uppercase Y to represent the random variable, or I'm sorry, the uppercase letter to represent the random variable, and the lowercase letter as a way to say, hey, this is one particular value that our random variable can take on. And so that's why I have in this table here the lowercase y's. And as you can see, 0 here, 0 here. This is how the lowercase y is actually used. So for example, maybe capital Y here is a random variable denoting how many computer-like devices that you own. A person could be observed to own, let's say, 3 devices or 4 devices, a particular value of number of devices that they have. In a generic manner, this is denoted by then the lowercase version of that uppercase letter. And as I have here in red, this distinction can be difficult for students learning statistics in a formal way for the very first time, unfortunately. And what makes it even more difficult is that many introductory textbooks, such as, for example, Ott and Longnecker's textbook for a course like this, we'll simply use lowercase or uppercase letters for both meanings in order to make it easier for students. Instead, what I like to do is actually make that distinction between uppercase and lowercase letters, because this will actually help, especially for those students who will be taking more courses later on in terms of statistics courses. Okay, so let's take a look at some notes here. So why is the term probability distribution used? Well, simply put, it shows how the probabilities are distributed for potential values of y. Now, since y can only be 0, 1, 2, all the way up to 9, then if I were to add up all those corresponding probabilities, then I get 1. Because you have to be one of those 10 different numbers. Another way we could represent this is the sum from y equals 0 to 9, the probability that the random variable y is equal to a particular value of y is equal to 1. Of course, I don't have a way to get like a number like 4.2 on my draws. Don't have a way to get a number like 1.7 on my draws. So for all those other cases that are not listed, those corresponding probabilities are equal to 0. Now again, a probability like the probability y is equal to 7 is what we expect to have happen if the experiment's repeated an infinite number of times. In our actual sample that we had, the probability that y is equal to 7 was actually just equal to 0.04. Now there's actually two different kinds of random variables out there. One's called a discrete, one's called a continuous. We are working with a discrete random variable, and this term is used to denote when you have a random variable that has essentially a finite number of possibilities. Here we have 10 different possibilities. We will learn about continuous random variables later in this course. Now, in the sample, we saw the percentage of times that we got a 0, that we got a 1, that we got a 9. And if you were to take a larger number of samples, then what would happen? What would happen to these percentages? Well, again, we have this probability distribution that helps us make that determination. As we take a larger and larger sample, essentially our sample is becoming more representative of what's happening in the population. So if I were to use my sample function again, but now instead of using a sample size of 50, I use a sample size of 5,000 instead, look what happens. In terms of the number of times that I get a 0, I get 494 out of 5,000, which is approximately 10%. How often do I get a 1? Well, 501 times out of 5,000, that's approximately equal to 10%, and so on. So now as we have that larger sample, our sample is becoming more representative of the population, and we are getting what we expect from this probability distribution. Here's also a histogram showing how the height of these bars is becoming more uniform across the different range there. Okay, some questions. Suppose another sample of size 50 is taken. Would you expect the same observed values for the sample to be found? Well, we've already seen that earlier, and I've already answered that. Well, what if, though, you had this probability distribution instead? You know, what would happen? So this is actually on page 8. Well, again, what this probability distribution is saying is that about 1% of the time you would get a 0, 3% of the time you get a 1, and so on. It just so happens that the way that these numbers are represented or distributed is a little bit different. If we go back to our hat example here, what I could do, for example, is have maybe 100 of these slips of paper, have one that has a 0 on it, have 3 that have slips have 3 slips of paper that has the number 1 on it, and so on. And that will show you how this probability distribution would be represented in that particular case. Some characteristics of probability distributions for discrete random variables. Well, excuse me. The probability that you observe a particular value has to be always greater than or equal to 0. Again, notice this right here, that equal sign is in there. All probabilities are less than or equal to 1, and all these probabilities add up to 1. We actually saw an example of that earlier. Very often, you will hear people represent or refer to probability distributions for a discrete random variable as a probability mass function. Now you might be wondering, why are you introducing even more terminology here? Well, the reason is because this is an introductory stat course, and after you get done with this stat course, you're going to come across a number of different terminologies to mean the same thing. And so that's why I try to let you know what those terms are. Okay, so with that then, that concludes this introduction to probability distributions for discrete random variables.